Hello, I am Maria Paula, and this is the presentation of the work entitled An Experimental Validation of a Thermoelectric Generator LTspice Model for Energy Harvesting, whose authors are Mariana Marques Ferreira, Maria Paula Medeiros Gomes Miguel, and Cleonilson Protásio de Souza from the Federal University of Paraíba, and Orlando Baiocchi from the University of Washington, Tacoma. The presentation is organized as you can see. Firstly, we are going to discuss the introduction. In the second section, the proposed tag model will be described. In section 3, it will be described the parameterization of the modeled tag. And in section 4, the experimental results will be shown. Finally, in section 5, the conclusions will be presented. The crescent use of natural resources is damaging the environment inasmuch as the extraction of these resources can hugely reduce them on Earth. This is particularly true for petroleum, natural gas, and coal that are primary energy sources and that are not renewable. In this context, research on renewable sources has been conducted for the generation of energy to power high loads, from household appliances to buildings, cities, and even countries. However, renewable energy sources can be also applied for powering low small loads, like electronic circuits, sensors, and other low-power devices. The term that is related to renewable energy sources for low-power devices is energy harvesting. It characterizes techniques of collecting energy available around the device from sources such as light, heat, radio frequency radiation, mechanical vibration, and others. This energy is converted into electrical energy to feed low-power devices. As you can see in the figure 1, to carry out proper energy harvesting, energy transducers, energy conditioning circuits, and energy storage devices are used to supply regulated voltage levels to the load. One of the most important kinds of energy available in the environment is thermal energy, given that it can be found in several places in our daily life, as in some parts of moving cars, industry machinery, building walls and roofs, and many others. In short, it is possible to say that in thermal energy harvesting, a temperature gradient is going to generate electrical voltage through thermoelectric effects, as it is shown in figure 2. There is a transduction device that converts directly heat into electrical energy, that is the thermoelectric generator, as known as TEG. A thermoelectric generator is composed of a set of semiconductor pairs of N-types and P-types, connected electrically in series and connected thermally in parallel between a pair of ceramic plates, as shown in figure 3. The applied heat through the tag produces a temperature difference that generates an electrical voltage on the tag's LEDs based on the CBAC. A very interesting application of a tag-based thermal energy harvester is the harvesting of thermal energy from a tree to feed sensors that monitor the tree itself. This application is called Smart Tree and has been proved that it can generate a useful electrical energy due to the thermal gradient from between the temperature of an internal point in the tree trunk and the temperature of the bark. In this way, a sensor can be fed with energy from the tree and no chemical battery is disposed of into the environment. Figure 4 shows an image of the smart tree supplying electrical power to a wireless sensor. A way to carry out more experiments and get more results without the need to be in a forest or outdoors is through a thermal emulation platform that was developed to generate any actual thermal pattern of temperature difference and to apply it on a tag. In this way, it is possible to obtain a temperature difference from any potential thermal source in an environment, to apply that temperature difference in the platform to get the generated voltage and to evaluate if this source can supply enough energy to feed the sensor. As a matter of fact, the sensor is actually fed by the tag-generated voltage if, of course, the thermal source is capable of providing that. The figure 5 shows the thermal emulation platform. So, in this work, a tag model for a SPICE-based analog electronic circuit simulator is proposed to allow previous studies on tag-based energy harvesting system. The SPICE-based circuit simulator is the LTspice, one of the most widely used SPICE software in the industry. Additionally, an experimental validation of the proposed tag model is described considering the actual experimental measured data from the smart tree. The behavior of tags when they are exposed to a temperature difference can be inferred by some SPICE models. However, most of these models do not have symmetrical structure, considering their electrical schematics, and consequently these are not very adequate to access the tag-modeled thermoelectric phenomena in the energy harvesting process. Another difficulty of modeling tags is that their manufacturers in general do not make available the complete tag parameter values. Then, models in which some parameters can be abstracted are necessary. An example is shown in Figure 6, where the tag model is split in a thermal part and in an electric part. The electric part consists of three components: two voltage sources, V1 and V2, and one active resistance. When a current flows from P to N, the V1 voltage source absorbs energy and the V2 voltage source generates energy as heat, emulating in this way the Peltier effect. This effect is characterized by an electric current flowing through a thermocouple and producing either a heating or a cooling effect depending on its direction. This heating or cooling process provided by the V1 and V2 voltage sources can be observed also in the thermal part as they relate to the current sources. As known, when the ends of a given PN junction are subjected to a temperature difference, a voltage difference appears between these ends. The commercial TEC 12706 model tag was chosen to be assessed. It is composed of 127 semiconductor pairs of bismuth telluride soldered on aluminum oxide strips. Its performance specifications are described in Table 1. The tag model requires four parameters: the Seebeck coefficient, the electrical resistance, the thermal resistance, and the thermal capacity. To compute the Seebeck coefficient and the electrical resistance from the tag datasheet, the following steps are needed to be followed to obtain these values. Firstly, it is necessary to get the maximum output voltage from the datasheet. For the model used, the maximum output voltage value is 14.4 volts for a hot side temperature of 25 degrees Celsius. Later, it is possible to calculate the Seebeck coefficient using the data from Table 1. It's obtained 48 millivolts per Kelvin. After, the maximum performance for a zero temperature difference is determined, and with this value, it is possible to obtain the electrical resistance also using the data from Table 1. The obtained value is 2.07 ohms. The model is demonstrated along with parameter values in Figure 7. With respect to the thermal parameters, the thermal resistance of 3 Kelvin per watt and the thermal capacity of 15 farad have been considered after a temperature variable test validation. Nevertheless, some tag manufacturers do not provide specifications values enough to characterize the device behavior or to determine these values under certain conditions, such as open circuit. However, the tag specifications values vary according to the load conditions. The Seebeck coefficient is the ratio of the generated thermoelectric voltage to the temperature difference on the sides of the tag. The open circuit Seebeck coefficient is considered constant, and the Seebeck coefficient for a given load resistance can be computed from after the system goes to steady state. Figure 8 shows the Seebeck coefficient for different values of load resistance. It is noted that the higher the load resistance, the higher the Seebeck coefficient. To validate the LTspice model for TAG, it was used experimental data from the SMART tree. These data were obtained between August 2nd to 5th, 2019, considering the internal temperature at 100 millimeters depth and the external temperature as shown in Figure 9. As can be also observed in Figure 9, the obtained temperature difference has peaks of 1.38 degrees Celsius and minus 3.47 degrees Celsius. The generated voltage when the temperature difference was applied on the thermal emulation platform as open circuit on a test scenario, as can be seen in Figure 10, where the blue curve represents a temperature difference and the red curve represents the respective TAG generated voltage. The thermal gradient introduced previously was applied on the thermal emulation platform and in the LTspice model for the following test scenarios. Each test scenario has a Seebeck coefficient and load resistance value. The test scenario 1 results are presented in Figure 11, where the red curve is the TAG model voltage values and the blue curve is the TAG measured voltage when the temperature gradient is applied in the thermal emulation platform. It is observed that both curves are similar. For test scenarios 2 to 5, the Seebeck coefficient values with their respective load resistance values were applied to the LTspice model of thermoelectric generator, and the simulation and emulation results are shown in Figure 12, where the red curves represent the voltage values obtained by the TAG model and the blue curves represent the voltage obtained experimentally. To evaluate the precision of the TAG model in comparison with the real performance through the thermal emulation platform for different test scenarios, was calculated the root mean square error for different situations. Table 2 shows the results for the test scenarios and the root mean square error achieved. From these results, the minimum root mean square error was for test scenarios 3 and 5. In this work, a TAG model for a SPICE-based analog electronic circuit simulator was introduced. The actual temperature difference from the SMART 3 was used to validate the TAG model. Therefore, the TAG model can be used in energy harvesting applications to obtain a preliminary evaluation of the energy generation potential. Using different Seebeck coefficients obtained from the TAG datasheet and from experiments, the use of the TAG model shows to be more accurate. In this way, made possible to evaluate the potential of all the energy sources. And thank you all for your attention.